one of the amazing secrets to Fred's success is that my own experience is very good with people and he's very good with people. My real first contact with Fred was in 1996. I just finished my PhD, just moved to Boston, and he invited me to a colloquium. So after the colloquium, instead of taking me to a colloquium dinner, he took me home and made me dinner. I would never forget that. That was 21 years ago. And to this day, I can still actually remember the vegetables. We actually went to the market and bought food. I'm Cantonese, he's Cantonese. He says, my wife Helen, let's go make some da bingo. It's a Chinese hot pot. I didn't know that Urbana Champagne had a Chinese grocery store. We bought food and we had a wonderful meal. And instead of putting me in a hotel, he had me sleep in his son's room. It was very good to finally meet one of them. I don't know whose room it was, but I spent the night in his house. So that's the kind of impression you never ever forget. The second little thing I'd like to share is that none of you know actually how to pronounce my name. My first name. The only two people that I know who know, one is my father, and the other is Fred. And for the last 20 years, Fred has never missed a beat. Well, actually, my name is Portuguese. Okay. He knows how to pronounce my name. And the third is how I came to now work in the Academy Institute in Beijing. I would say that's 95% due to Fred. The chair of the search committee was Bob Williams. Bob Williams, which I remember sitting in Carnegie and said, oh, no way on earth. And everything and moved to China. And then Fred started calling once and twice. So just put an application and just trying. And then Paul was in the committee and he interviewed me. Anyway, one thing led to another, and it's very persuasive. So now I've given up my job at Carnegie and moved to the Science Institute. This is the KIAA Institute. The first thing I did was to ask Fred to join the International Science Advisory Committee. So there he is. And the KIAA at SAC is actually very active. They don't just advise, they really tell you what to do if you're not doing it right. So this is one of the most important bodies that helps guide me through the many challenges I face, but not just in a formal way. So this is the formal capacity. But in the last 3 years or so, I cannot remember how many times I've Skyped with on moments of utter panic, emergencies, and things I just cannot solve. There are basically two people professionally that I call, and Fred is one of them. Depends on who picks up the phone. I can't actually very hard to imagine not being able to call Fred. He and I have only co-authored one paper, but it's one of the best papers that I've ever written. At the time before ALMA, this is the highest resolution CO image of M82. We had managed with subarc-second resolution with OVRO detect a population of clouds that we argue are the progenitors of the superstar clusters, which are the analogs of globular clusters. We detected a population of these clouds with an angular physical resolution of 725 parsecs. But we did not collaborate beyond this one paper. So I'd like to tell you is a collection of things that my group now in Beijing is working on, but I think Fred would like. Okay, one way or another, these are topics that Fred has touched early in his career. Beginning with black holes themselves. Reinhardt will give you a full talk about the galactic center, so I will not talk about the galactic center, but as you know, the field of supermassive black holes is entirely driven, historically, by the dynamical detection of supermassive black holes. The best case is the Milky Way that Reinhardt would cover. The second best case, besides the Milky Way, of course, is the use of water lasers. with a water line at 22 gigahertz and VLBI techniques, you can reach sub-parsec resolution for nearby galaxy. This is very famous NGC 4258 megamaser. Of course, this field was really driven early on by this important paper by Clausen and Lowe in 1986. And then the CFA guys and the Japanese group using VLBA took it over. That's really the historical influence of Fred. This is before HST came online, and of course contributed the bulk of the statistics that has led to this phenomenal result that has driven the field in the last 15 years or so. The discovery that once you plot, right now there are about 100 black hole masses dynamically detected, but they have a very tight correlation with the bulge property, particularly the host galaxy property, particularly the mass of the bulge. This unexpected result has led to literally, this is the paper that launched thousands of papers, and it's made people invent the whole concept of AGN feedback and energy feedback in galaxy formation, either via radiation or via radio jets. This has now become a standard part of the toolbox for galaxy formation people. But there's actually a lot of missing holes behind this otherwise very popular field, because we really don't know when and where and how, in fact, this correlation was established. People know in theory using computer simulations, but in observations it's very difficult, because you need to understand that this correlation was established at redshift 0 using black holes that have finished all their activity. These are dead black holes, like the Milky Way, for example, or M87. These are black holes that are no longer growing. This is the end state of their lives. To really understand where, and how this was established, it's actually imperative to search for the seeds of things that eventually grew up to be the most massive black holes. So a very active field of research is so-called intermediate mass black holes, other things below 1 million solar masses, but greater than, say, 30 or 100 in galactic nuclei. At the same time, what are the most massive black holes that nature can make? The record holder so far, Changpei, who's somewhere here, is 21 billion solar masses. Are there any that are actually more massive than this? If you look at the most luminous quasars at high redshifts, by the luminosity, they may actually imply masses larger than that still. And of course, how do you get from here to there? For that, you need observations at various redshifts to piece together the life cycle and the growth history of black holes. But to do all of this, you really have to abandon this cherished M-sigma relation for normal galaxies. Okay? There's no way to answer these questions if you do not go to galaxies where the black hole is still growing. That is active galaxies, AGNs and quasars. Okay? So for quasars, you need to basically measure the same quantity on the x and y axis. Black hole masses and essentially the gravitational potential of the host galaxy, or whatever it is you can do on the x-axis, because it becomes very challenging by the time you reach redshift 3, 4, 5, 6, 7 to detect anything about the host galaxy, but you must, okay? And apart from just establishing this type of correlations for active galaxies, a useful way to think about this is to actually ask how does this diagram evolve dynamically? That is, can I take the time derivative of the x and y axis instead of the black hole mass? What you really would like to know as well is the mass accretion rate in solar masses per year. Don't just tell me what is the Eddington ratio. That doesn't tell me what is the accretion rate. Okay? And instead of the final galaxy mass, can you tell me what is the growth rate? That is the star formation rate. Now, these things you might think are relatively standard to do. This is what extragalactic astronomers do every day. But in terms of active galaxies, it becomes extremely challenging. As I'll try to convince you, personally, I don't think that we have been able to obtain any reliable measurements to date. This is in my opinion, a completely unsolved problem. The challenge lies here, because you're not dealing with galaxies like this, where the black hole is inactive. You're dealing with galaxies like this. They're quasars. The quasar in the center really screws up everything, absolutely everything. Okay? You cannot use traditional spatially resolved dynamic techniques to measure the mass of the black hole. Okay? You cannot see the stars because you're blinded by the quasar. You cannot trust the gas because it's being blown around by radiation pressure. You can hardly see the galaxy at all once you put it at high redshift. Forget about measuring reliable masses because everything is just badly blended. So this is the observational challenge, but I'm going to show you that we've made quite a bit of progress, and there's a large group, particularly in China, that is focused on this. Another very important question is this, whether this whole concept of AGN feedback is correct at all. Okay? Most of the papers you see, and there are lots of papers, rely on hydrodynamical simulations like this, where you imagine in gas-rich mergers, when the gas goes to the center and the black hole turns on, the black hole does catastrophic things to the ISM of the host galaxy. Okay? The interstellar medium is ionized, rearranged, blown out, such that you can shut off star formations, such that you can self-regulate the growth of the black hole. No matter what the details of this type of scenario, this is an unavoidable prediction of any effective feedback model. The interstellar medium content and dynamical state of this object absolutely cannot be the same as the progenitor. So this leads to a testable prediction if you can measure the cold interstellar medium kinematics and content of quasar-host galaxies. Moreover, one really should think of quasar-host galaxies as just galaxies. Okay? They're just galaxies that happen to be on, at that particular time. So once you've measured the gas, once you measure the star formation rate, once you measure the stellar mass, they better be interpretable in the framework of what we know about the galaxy population. That is, how do quasar-host galaxies behave on this cherished Chemical-Schmidt relationship between star formation rate and gas, right? And these various very well-behaved scaling relations, which we now understand better and better for the normal galaxy population. That's the context in which one should think of active galaxies. Of course, all of this requires observations across the electromagnetic spectrum, using a variety of techniques to probe different components. But there's a huge challenge. You see, the broadband SED, even just focusing on UV to the far infrared, is already tough enough, even for a normal galaxy, right? This is just a regular old galaxy. You have stars of different ages, okay? You have dust of different temperatures. You have, in the mid-infrared, these very complicated features called PAH features, polycyclic aromatic hydrocarbons. It's already bad enough to try and disentangle all of this. But now I'm going to turn the AGN on. I'm going to make the nucleus active. And gosh, everything is really, really bad now. Okay. Essentially, every comfortable diagnostic you can think of for normal galaxies is destroyed or hopeless. Okay? Just forget about it. Okay? You can hardly see the stars, and if you can, all the colors are screwed up. You have this hot dust component coming from a torus or whatever that's going to totally change the spectral shape, contaminate all these lines. And even the far infrared, you're not immune from synchrotron emission because as a jet, as many AGNs do. But the challenge, therefore, is if I give you a real data set for an AGN, is can you decouple all of these components? The fundamental parameters, I think, are most interesting on two scales. On the central engine scale, we want to refine and improve our mass measurement technique. We want to measure the entire broadband spectral energy distribution. That's key to getting the volumetric luminosity. You want to fit accretion disk models to that SCD so that you have some hope of actually deriving mass accretion rates. In the case of the galaxy, we want to measure the things that we measure for galaxies. Stellar masses, internal kinematics, the distribution of the mass, if you like, the morphology, right? And extremely crucially, I would argue, is the cold interstellar medium component, which is I think this is one of the new key things that have previously been essentially untouched. And finally, the star formation rate, which I'll emphasize again, is extraordinarily difficult. All of this is mediated by gas. Gas is the raw ingredient to form stars, it's to do accretion, so you want to measure it, and then you want to measure it as a function of time. Okay, from the nearest objects out to redshift 7 and beyond. I want to just emphasize a few of these aspects in the interest of time that particularly my group has been working on recently. So in terms of black hole masses, the traditional way to do this for quasars and AGNs is due to the gentleman on the front row, reverberation mapping, influential techniques paper by Blanford in 1982. The key is that even though you cannot directly, spatially measure the size of the so-called broadline region spatially, okay, what you can do is you can try to measure it temporally. The key is that in AGN, the continuum goes up and down for various reasons that are not well understood, but so do the emission lines. The emission lines go also up and down in pretty much the same way, because the emission lines are photoionized by that continuum. But there is a time delay. There is a lag due essentially to the light travel time, and that if you can measure that time delay with monitoring observations, then you can try to figure out the size of the broadline region. Okay, the velocities you can measure directly from spectra. What is missing is a normalization factor that accounts for the detailed structure, kinematics, and indeed inclination angle. But this is a disk. This is a very large industry internationally, and one of the newest competitors is a team in China that is now embarking on reverberation mapping in a very, very big way. Okay, we effectively have taken over at least two and a half of these telescopes, actually several telescopes. We have between 70 to 100% of the time. That we're going to devote roughly 5 years to do this problem extremely carefully, not just in quantity, but also in terms of data quality and also analysis techniques. But it's my feeling that no matter how hard you try, how big your samples get, I am very dubious whether we can actually obtain the mass of the black hole to better than a factor of 2 to 3. And the reason is this nagging factor F that we don't know. Okay, at the moment, in order to constrain this factor F, it comes from calibration with normal galaxies. So for the subset of objects that have both reverberation mapping and a measurement of sigma, for example, we insist that they have to lie in the same M-sigma relation to solve for this factor F. But the trouble is that there is an intrinsic scatter of about 0.3 dex or larger, which is essentially an irreducible intrinsic uncertainty. You might think that if you can get very high quality data to get what's called velocity resolved delay maps, such as these, then you can try to solve for the structure and the kinematics directly. But it's actually incredibly difficult for the simple reason that there's no known independent way of confirming, independently checking whether these models are correct. You're going to get a solution that you actually, how do you know that these masses are correct? I think there's now a potential breakthrough that's unexpectedly offered by ALMA. This is something that my collaborators have stumbled upon, and I don't think it was entirely anticipated when ALMA was planned. You see, galaxies not only have maser disks, those are very useful, but they're extremely rare. Much more common disks in CO. Okay, so these are HST pictures of nearby giant elliptical galaxies. 25% of them have gas and dust in the center, and often they're arranged in these very, very nice, quite thin circumnuclear disks. The scale here is about 100 parsecs or so. Okay, so with ALMA, don't forget, ALMA has 10 times the resolution of the Hubble Space Telescope, And you can probe this thing with various transitions of CO. You don't need to wait for it to maze, right? Mazes are very rare. CO is very common. This is the first demonstration. This paper achieved a resolution of 0.044 arc seconds. This is CO 2 to 1 for one of these nearby objects. Okay. This is the full, integrated CO distribution. That's the size of the alpha beam. Okay, so you can see we very, very well resolved this disk, both in minor and major axis, line of sight velocity, velocity dispersion. This is a model that takes into account all the instrumentation effects. And without doing any fancy statistics, you can do the reduced chi-square in your eyes, right? It's 1. Okay? It's almost as good as the masers. We can get the black hole mass, in this case, to an accuracy of 6 or 7%. And this is only a resolution of 0.044. That's already very good. That's already a factor of 2.5 better than HST. But we can do a factor of 3 better. Okay? So now we've gone crazy. We have, the TAC has been very nice. We've gotten time in every cycle, grade A. And we have a building up sample here, a bunch of more cases. And we're going to get a lot more. Okay? So this is a new mass measurement technique that's completely opened by ALMA. And obviously, the obvious tribute here goes to Fred, for having taken a role in making ALMA possible. In terms of MDOT, the key is to get simultaneous, broad spectral energy distribution coverage from optical UV all the way out to X-rays. So this is a matter of data collection. You need to know the mass of the black hole. So if you know the mass of the black hole, then you need models, not just standard disks. You need to consider whether they're relatively inefficient disks or whether they are super Eddington disks. So you need new generations of accretion disk models to match to these data with the black hole mass known. Then you have some hope of extracting the black hole mass in solar masses per year. I've not yet attempted to do this, but this is something that we're aiming to do. The host galaxy is very, very challenging, even for relatively nearby quasars. There are basically 2 ways. We want to measure the stellar mass of the host galaxy and the dynamical mass. The stellar mass absolutely needs something like HST in order to remove the nasty point spread function and have a good two-dimensional model of the galaxy, which can be quite complicated, but this can be done using techniques such as GALFIT. More relevant to Fred, you can use radio techniques. So here's an experiment I tried 10 years ago. I tried to be a radio astronomer by using Arecibo. You can detect H1 out to very nearby redshifts, say 0.1, 0.2, thereabouts, okay? The key is that simply by measuring the width of the line and with some constraint on the size, you can attempt to estimate the dynamical mass of the galaxy. Of course, this is where the new Chinese 500-meter telescope should become a very important tool. It allows us to really do this on a big scale. The star formation rate, why is it so difficult? I alluded to this several times, okay? Because of all of this contamination from the AGN. We're going to use 4 independent techniques. I don't know whether any of them will work, but if we can't do it, then others haven't done it either, but we will try. The 4 techniques are we're going to make use of these pH molecules. They are very abundant. They are always there in these high-quality Spitzer spectra. What has been lacking is a good technique to measure them. Just because it's strong doesn't mean you can measure them well. Because there's no continuum. Actually, how to fit these lines turns out to be, we don't think anybody's ever done it properly, so we're going to do it again. We're going to use these neon lines, these ionic lines, which is another way that we can get a star formation rate using a technique I invented 10 years ago. Finally, we're going to use the C+ line from Herschel packs. The C+ line is one of the dominant coolants of this meeting, comes from the PDR. It can be traced to the star formation rate as well. And finally, the far-infrared continuum. But in order to measure the far-infrared continuum, you absolutely must decouple all of these nasty overlapping components, and you need to do it all self-consistently and very, very carefully. So all of these things are now being done by my student, Shangwan. In terms of cold gas, I already mentioned H1. We're also using ALMA in a big way. We're surveying a large sample of quasars, nearby quasars, using ALMA, particularly the compact array, simply for to make robust detections. But I'm really most excited, believe it or not, by dust. Dust is a very underappreciated way to measure the gas. You see, the dust modulo one parameter, which is the dust-to-gas ratio, gives you the total cold interstellar medium, that is H1 and H2. Okay? And measuring the dust, which is simply a photometric measurement, is not that trivial, in fact, because you need to get broadband photometric measurements, including beyond the Rayleigh, into the Rayleigh gene scale, but you can do it. Measuring the dust photometry is much easier than detecting H1. H1 is not currently detectable beyond a very local universe. In CO, you have to get rid of this, conversion factor that people still debate about, the factors of a few floating around. But gas gives you, the dust gives you the total gas modulo the dust-to-gas ratio, which is not a free parameter. It's only half a free parameter, because the dust-gas ratio scales with metallicity, which scales with mass. So if you know the mass of the galaxy, you can backtrack this, I think, to get reasonably accurate dust masses. You need to be able to analyze the data in a more intelligent fashion by taking into account all of these complicated things. But the bottom line is we can finally measure dust masses and gas masses for significant samples of quasars and compare them in the same way that normal galaxy formation people do for normal galaxies, which are these blue points. Okay? So all of this work is done in the context of a very large new project funded by the Chinese Ministry of Science and Technology. It's an obscenely large amount of funding that the Chinese government is investing in basic science, and this is one of them. The team has about 100 people, and we're going to spend the next 5 years working on this set of related problems. And a key component here is FAST, which, as you all heard, Fred has actually played a role even in China. Yeah. So that's it. Thank you.
Thank you, Louis. Questions?
Thank you for the talk. You commented on difficulty of measuring star formation rates in AGN, and you mentioned that mid-infrared lines such as pH and other ion lines could be very helpful. Would you like to comment on how JWST in the future could help with these star formation rate measurements?
Very good question. JWST, in terms of wavelength coverage, I think of JWST, at least for my work, is simply a very high resolution spitzer. Okay, so the wavelength coverage, can go up to 30 microns. You have a resolution about 3,000-4,000. Okay, so that's very good. That means you can resolve all these blended lines quite well. The key, of course, is now you have very tiny beam. Okay, so for luminous AGNs, it's not going to do anything different. There's no need to use JWST. But then for less and less luminous objects, that is objects with lower and lower accretion rates, where you absolutely must zoom in to disentangle the nucleus from the host galaxy, JWST would be very key. Okay, there are several teams that have actually proposed to already to do that for early science with JWST. So that's I think the most interesting application.
Louis, great talk. As somebody who started his career working on normal galaxies, I've always been puzzled, how these two communities of active galaxies and normal galaxies had nothing to say to each other. I mean, I could meet Roger Blanford and we wouldn't have much to talk about it in the old days. So it's great to see you unifying these two subjects. I was interested to see your circumnuclear disk rotation curve. Is it Keplerian or is there a non-Keplerian component to it?
The cases we've analyzed so far are very Keplerian.
It's what?
Very Keplerian, yeah.
It's very Keplerian.
Yeah.
Second, I noticed many of your images actually show spiral galaxies. It's interesting that spirals appear so early in a galaxy evolution. Okay, given so there may be further integration. Okay, as you probably know, there's been a lot of work on spiral structure in galaxies, and that can add added
Yes.
information.
In fact, there's been a lot of emphasis in the AGN community on the bar, okay, because it's a very obvious way to redistribute angular momentum and lead to so-called secular evolution in even in isolated galactic disks. That's been a very popular subject, but the spirals, I absolutely agree, have essentially been largely ignored.
Well,
Like,
bars and spirals are the same. That's been integrated, okay? So,
But I meant in terms of the
it's the same.
influence, in
It's
terms
the
of
same
the
mechanism.
influence of spirals. Okay, I'm blaming the observers now. Okay, you're absolutely right. In fact, I have an entire PhD student working on spirals for this very reason.
Right.
Could you say a little bit more about what is known about the evolution of classical bulges, the outer redshift of a half or so?
Out to a redshift of a half. I think what is known is that they were established much earlier than that. Okay, so the evidence so far is that classical bulges are basically little elliptical galaxies in almost every way, including their formation epoch, which is basically redshift of 2 and higher, and also their formation mechanism, which is fast and highly dissipated. It's fast. The fast comes from timing estimates that come from alpha to ion ratios, the ratio of type 2 to type 1a supernovae. If you believe the modelers, it was as quick as half a DPU, okay, or something like that. Okay, so the story is very similar to the giant elliptical galaxies. So there was an early phase, an early rapid phase, and in my mind, that's also the phase that was associated with the real birth and growth of the massive black hole. But then, of course, a lot happened in the last 10 gigayears in acquiring the disk in the case of spirals, and in growing the envelope in the case of ellipticals. So there's sort of a so-called two-stage or two-phase scenario. That's my understanding of classical bulges.
If you look at the mass of the bulge or the velocity dispersion of the bulge out in an individual galaxy, how does that evolve over time?
It actually slightly decreases over time. Because again, the two amazing things about this early rapid formation phase, okay, it made this extremely dense thing, most likely due to cold flows, not always major wet mergers. The velocity dispersion, so it's very dense, so the velocity dispersions are very large. But over time, the density actually decreased by things accreting onto it, by minor mergers hitting it without much gas dissipation. So the size grows, and the velocity dispersion actually slightly decreases with time.
Is that an observation or a theory?
That's what, in the case of massive elliptical galaxies, that's an observation. Those are very challenging because you must measure velocity dispersions at redshift of 2 to 3, and some people like Peter Van Dokkum have spent 30 hours on the VLT to make a single measurement. But these things are slowly accumulated. I think may also be some theory work behind this. Chen Pei has done some work on this, I believe, along with the Elliott Clark.